All right, and we're live. Good morning, everyone, or good afternoon, or good evening, depending on where you're watching in from. Thank you all so much for joining us as usual. Today is really exciting for me because, as we've discussed, all of our code is open source now on GitHub, but we have limited docs available online, which I can share later. But now is going to be the first time that Mike actually goes through the code base and just does a deep dive on how everything works. So with that, just a couple housekeeping things. If you have any questions, feel free to put them in the chat. We'll just pretty much address them as they come as we have time to. But with all that said, Mike's just going to go ahead and share his screen and walk through the code. Um, I'll let you take it from here, Mike.
Cool. Yeah, sounds good. Thanks, Justin. Yeah, so this will be just kind of like I'll start with a high-level walkthrough of Brink smart contract code, and then maybe get into a little more detail. I'll pretty much go through all the detail on this call or on this live stream. And yeah, Justin, let me know if there's questions because I'm going to be sharing, so I probably won't see them.
Sure, I'll be
But yeah,
monitoring. Yep, I'll just chime in whenever there's a question and whatnot.
yeah, this is really exciting because I think like this is probably the most detail that you'll have gotten on the code base, Justin, because usually we're having higher level conversations about all sorts of other things, but this is just focused on smart contracts on the protocol side. Coincidentally, we just started an audit for this code, so I'll be going through the code that we're using for that audit. We just basically tagged a kind of starting commit hash for that. So this is pretty close to the code that we'll be deploying on mainnet, hopefully, unless we kind of uncover any critical issues, or I'm sure there's going to be small things that we need to patch, hopefully nothing big. And I think it's good that we're doing this live stream now, just like talking through the code base. This is great for like anybody who wants to understand Brink, how Brink works, how they could potentially integrate with Brink. Just probably a good overview of the whole system. And also, if anyone can use this information to like find a bug or vulnerability, like that's good for us. So the more attention we get on the code, the more review, the better, especially pre-mainnet deployment. So I'm just going to share and start going through this. So I'll just be looking at this on GitHub. So 2 repos to focus on here. We have a few more on Brink Trade. So yeah, I'll just back up a second. Our GitHub is /Brink Trade.
I'll go ahead and post that in the chat here.
Okay, thanks, Justin. And there's a few different repositories here. I'm going to go through 2, which are the Brink core repo, which is, as you might guess, kind of like the core smart contract repository for Brink. And then another repo called Brink Verifiers, which is basically like sits outside of core. These are basically smart contracts that verify signed order types. So this is kind of like the verifiers that we've created, and then there could potentially be more verifiers created in the future. But this just has like kind of the first verifiers, and that's really like the limit order verifiers. So I'll go through those in more detail. So
and just
yeah,
to clarify for everyone watching, we used to call them executors. Now we're going with the terminology verifiers. Is that correct?
We used to call them in the code base. Yes, we used to call them executors, but I think it was confusing because executors are like the role of actually like executing orders. So we were kind of like calling them verification contracts, and then at some point we just like renamed all of them to verifiers, moved them to their own repo. But they're really like, yeah, they just sit out. Like we could deploy potentially, or anybody could deploy many verifiers. So there could be someday like thousands of verifiers. They correspond to order types in the system. So like the first order type we have is limit orders. They need to be verified, like signatures for those limit orders need to be verified before they're allowed to be executed. So the verifiers are the contracts that do that. Okay. So I guess I'll start with Brink Core. So let's just jump into that. So if you're in Brink Core, pretty standard smart contract repo. I won't go through the details of the repo itself. I'll just jump right into the contract side of it. So we have a few different directories here. In our repos, you'll see like test. Test is all just like for the purpose of unit testing these. It's nothing that will be deployed on chain. Everything else, there's like a mix of kind of contracts that will be deployed and contracts that like are used for inheritance, interfaces, etc. But the kind of the core of the core repo is the account directory here. So account basically contains the logic for Brink proxy accounts, and the way Brink works is it's basically like a smart contract account that you're signing certain permissions for. So you have this account, you own it exclusively, you put assets into that account, and then you sign messages that basically allow the assets in that account to be manipulated based on certain on-chain conditions. So like in the case of a limit order, you would sign like your output amount of token, the token that's being output, the input amount of token, the token that's being input. So that's like basically your required output and input for a swap. You sign a message that allows that to happen if it can be sourced. And then what you're basically doing is you're signing a message that allows the account to be, that asset to be taken out, like asset A to be taken out of your account in exchange for a certain amount of asset B to be added to your account. So that's just like a simple example, but the way that the Brink accounts are structured, it allows that for basically like any condition you could think of. So I'll just jump into account.sol. This is like account.sol is basically like a contract that gets deployed once, and all the Brink proxy accounts point to this as like their kind of like logic contract. So if you're familiar with kind of like smart contract upgradability patterns, this follows like a pretty standard like Open Zeppelin upgradable pattern. I'll talk a little more about that when we get into the proxy side, but basically like this contract is meant to be like kind of the core logic for all accounts in Brink. So as I mentioned, gets deployed once, and then it contains basically like kind of a really low level like signer functions and like delegated functionality. So I guess I'll go through it from the top. I can start with, or I'll start with like the kind of like state modification functions. So functions that allow for state modification of your account. So external call is really there for like direct calls from the signer. So maybe to back up a sec, like the account has a signer, and that's you. That would be your address, some address that you own. Generally, if you're coming in through the web app that we're going to be deploying, it's going to be your MetaMask account. So your MetaMask address. Well, your MetaMask address kind of like exclusively owns your account, and if you see like proxy owner here, that's really like the owner of your account. So proxy owner is the address that owns the account. There's a lot of checks regarding proxy owner. There's a few functions in here that allow you only the proxy owner to call those directly, and those are kind of like if our web app or another web app interacting with Brink accounts needs to like provide some direct call into the account, then that endpoint can be used. So external call basically like allows the proxy owner to make any call from their account to another contract. So it just uses this like call opcode to basically like proxy or execute a call on an external contract outside of the Brink account. You give it, you can do like ETH transfers with this as well. You give it a value in ETH, the address of the contract that you want your account to call, and then the call data for that contract. And then I won't get into the assembly details just yet. If we have questions on that, maybe I could talk about that. But you'll see like kind of the same pattern or similar pattern for a lot of these. I could drop a link, or we can drop a link that explains this a little bit more.
Sure.
So external call is like, yeah, and Justin, I'll let you know what that is, but we can look that up in a sec. External call would be like, let's say I want my account to do like an ERC20 transfer. Like you would give it the value of 0 because it's not dealing with any ETH. The to address would be the address of the token that you want to do the transfer on. And then data would be encoded call data for the transfer function that contains the function signature, which is basically the hash of transfer and its parameters, and the value of the parameters you're passing. So like the recipient of the transfer, the amount of the transfer. And the client that calls this is responsible for kind of encoding that data. So that could be like a web application, or if you're using the Brink SDK actually does that and kind of like abstracts that encoding out a little bit. Or you could do it kind of manually and call this directly. So yeah, realizing this is a lot of detail. Like this is the lowest level of the code. I think for most people, like you would be using Brink SDK, which is still kind of like in progress. It's not as like stable as the smart contract code is, but we're still working on this and open to contributions as well. But yeah, I'll just point out that there is a Brink SDK. Generally, like if you're developing against or you want to build an application that uses Brink contracts, you'd be using Brink SDK. It's much easier than going directly to the smart contracts, but it's good to have an understanding of the kind of lowest level of Brink accounts as well. So that's what I'm going through now. So external call for like calling to an external contract. You can also use this for ETH transfers. If to address is like an EOA account that you're transferring ETH to, and call data is 0, like just empty bytes, then that'll do an ETH transfer. It does use this value to actually transfer ETH, and this would be executed in the context of your account. So you could use this external call to transfer ETH. You could use it to like create an LP position directly. You could basically use it for any action that you would take on any account on Ethereum. A delegate call is similar to this, except it just executes the call like directly within the context of your account. So it does call to an external contract, but it's going to operate on your account itself. So we could use this, and again, it checks like you can only call this directly as the proxy owner. So we haven't gotten into like the kind of meta like signed data execution of conditional orders yet. This is all just like account management stuff, I guess, like for if you are the owner of the account and you're calling in directly. So it does the proxy check, make sure that you're the owner of the account. And then what you can use delegate call for is like if you are changing state on the account itself, but you don't need to like do any external contract interaction. You basically give it a to an address of an external contract that contains the logic that you want to execute, but that's going to execute within the context of your account. So an example would be if you have some order out with like a unique identifier that's basically saying if, and we do that, I'll show you this when we get to verifiers, but we have kind of like a bit, a unique bit for the order, and that gets checked on the account, so on the account state to see like, okay, has this bit been set yet? Has it been used? You can use this to like write to that bit and effectively cancel an order that is signed with that bit. So that would be an example. Is you're manipulating some state on the account directly. It doesn't have anything to do with like external contracts like a token or another recipient or like a staking contract or whatever. It's just state on the Brink account. So yeah, that can be used really for any state manipulation on the account. But this is like what the SDK uses it for specifically is for cancel and like setting that bit. So moving on here, get down to the fun stuff. So up until now, that like those two functions were really just like, so you can, like you as the proxy owner could like make direct calls into the account. So you'd have to pay gas for that. Just like any transaction that you do through MetaMask or with a hardware wallet or whatever. Like it's just a simple Ethereum transaction. But where like the cool stuff happens is with these meta calls. So that this meta delegate call basically allows you to, or allows the proxy owner to sign a message that allows execution of certain things that the signed message specifies. So this is like super low level, like generic function. Doesn't have anything to do with like an orders specifically or value transfer. It's really just a function that says if the caller of this function to this account provides a signed message, that message was signed by the owner of this account, then like allow it to be executed. Like whatever's in there allowed to be executed. So there's a couple things in here. The message contains like basically an address that it's going to be executed to, call data for like what the message actually will execute or is permitting to be executed. And that's pretty much it. I mean, this is what's signed. This is what, when you're signing a Brink message, you're signing these two things. So then the caller of this meta delegate call is actually calling to your account. So it could be like anyone in the world. It's permissionless. They just call to this meta delegate call. If they can provide a signature that you signed, or that the owner of the account signed, then it will allow execution of this. So it's just like execute this data on this contract. There's also an unsigned data parameter that allows that like executor to kind of specify their own execution parameters, and then the verifier is responsible for making sure that unsigned data is used in a safe way. So you don't have to, like a verifier doesn't have to use unsigned data. If not, then this would just be, the executor would just have to pass in 0 bytes for this, or it would just basically get chopped off and wouldn't get sent to the verifier. Or it would get sent to the verifier, but the verifier would just kind of ignore it if if it's not expecting that. So we use a kind of, well, 2 signing standards, but the first one that meta delegate call uses is EIP 712. So EIP 712, you can just look it up. EIP 712 is a type data signing standard. Works really well for Brink because we have kind of like complex signing requirements. Rather than just signing like some random byte hash, EIP 712 lets us sign like actual type data with some structure. So you can through MetaMask you can see like what you're signing. I mean, it's still, I wouldn't say it's exactly like user friendly, but at least it's like showing some amount of data and not just like some random collection of characters. That's one of the advantages of this signing standard. But anyways, you can read more about that. EIP 712, that's kind of like what we use. That is what we use. If we look at Recover Signer, so that is just an internal method that we use. I guess I won't dive into it yet. I'll just like keep going through. If you guys want to separately look into Recover Signer, you can. But what this is basically doing is saying, get me the signer for this signature given this hash. So the hash is type hash for the function. So it's ensuring that you can only use the signature for this function, and then the signed data, kind of encoded and hashed together, pass in the signature with that hash, and it's going to give us the signer. And then if the signer is not the proxy owner, then we just revert the call. So if the signer is the proxy owner, then we allow the call to be executed. So give it a valid signature. It executes the call. It is a delegate call. So that means it's executing on the context of the account. So it can, it's basically going to do whatever this to address and this call data does. Like that's basically like another contract with some function. This is going to make a call to that function. It's going to pass the data that's in this call data parameter or this call data variable into that function. So you can see it's like basically a packed version of the signed data and the unsigned data. And this is important. We'll go through on the verifier side how a verifier handles kind of both these pieces of data. And I'll note here, like it can be a bad verifier, if you're signing to a verifier that is not secure and doesn't handle these properly, it can be like a catastrophic account event. Like it could result in total fund loss for the account. So the most kind of like outside of just the core being secure, like verifiers do also have to be secure. And we're like deploying some verifiers as part of our like kind of first mainnet deployment. We anticipate that like other verifiers will be created, but if you're interacting with smart contracts on like through some web application, like you run a risk of interacting with a smart contract that is malicious. Say it's the same thing with Brink verifiers. Like if you're signing an order to a verifier that is not trusted, or not that it's not trusted, like that it hasn't been audited. Nobody's used it before. Nobody knows what it is. You don't know what it is. You don't know what you're signing to. Then you're risking like losing not just whatever that signer is telling you to sign related to. You're risking loss of your entire account because the verifier basically has full control over your account within the scope of what it does. So as long as it's secure, then it does what it says it does. Well, it always does what it says it does. But if you know what it's doing, you sign to it, then you can be assured that it's not that it's only going to kind of manipulate the things that you're allowing it to manipulate explicitly. So that's kind of important to note. I will go through verifiers after I get through this contract. So we have, that's basically like meta delegate call is probably like the most commonly used thing in Brink, and what we use for like all order types right now. And yeah, it just lets you use an EIP 712 signature to sign some conditions allowing like manipulation of your account in a tightly scoped way, tightly scoped to this address and this data that you're signing. So moving on, there's one other signing standard that we're supporting, and I'm really excited about this one. We actually just added this. This is EIP 1271. So basically, like same rules as the EIP 712 that I just described. Only this is for smart contract accounts as the signer. So whereas previously in the meta delegate call with this EIP 712 recovery, you the proxy owner has to be like an EOA or externally owned account. Proxy owner will sign that message using basically like a smart contract can't do it. Like that's what I'm trying to say here. The EIP 712 only works if proxy owner is an externally owned account. With EIP 1271, the proxy owner can be a smart contract and actually like not sign the message per se, but like basically it calls back to the smart contract to check the validity of the signature. So it will pass the signature to the smart contract and then verify it. So the reason why this is cool and why we added it is because we can support like Gnosis Safe, for example, as the signer of a Brink account. So we could support Gnosis Safe or really any smart contract. So you could have like some governance process through a DAO sign a limit order on Brink, or like Gnosis Safe multi-sig holders kind of collectively sign a limit order on Brink, or limit orders are just the start. It could sign really like any automation action through a Brink account. So yeah, you can read more about EIP 1271. Super cool. Glad it's in here. I think it's going to be kind of like someday a significant amount of activity on Brink accounts. We're not going to support it through the web app. It's more of like a kind of lower level dev thing for now. Stuff that's on the Brink web app when it does get launched will be primarily just meta delegate call signing and like kind of catering to Brink users that are using EOAs as their proxy owner. So that's a lot of detail on the core side. Pretty much, let's see, if I go back to the contract level, yeah, so account is kind of the core logic for accounts. I just went through all of that. As I mentioned, that just gets deployed once. And then if the actual owners of the account will have proxy contracts. So proxy contracts point to the kind of core account. So I'll just go through that. It is like custom, I guess, like we built this proxy specially for Brink. It's like kind of a super optimized proxy. It follows like Open Zeppelin delegate upgrade pattern. I can look up this. Let's see, Open Zeppelin proxy upgrade pattern. This is actually, let me look for this article. Upgradability, the state of smart contract upgrades, Open Zeppelin blog. This is an awesome blog post on smart contract upgrades. Justin, you want to post this in the chat? You want me to send this to you?
Sure, yeah, if you can send it to me in the private chat, I'll post it.
Okay, well, I got to stop sharing my screen.
Maybe no worries, I'll Google it then.
Yeah, it's just the state of smart contract upgrades. It's an Open Zeppelin blog. You can post that. So that's a good article for describing like many different proxy upgradability patterns. Now, often like you'll see proxy upgrade patterns in the context of like upgrading a whole protocol or like kind of like macro upgrades, where, I don't know, like you could deploy, let's say, an AMM contract and then have some like upgradability backdoor for that, where like the team that deployed it could like upgrade the contract and change it all. Like that I believe is a poor use of the upgradability pattern. Like you don't want, like we don't have anything in Brink that allows the Brink team to upgrade the contracts after they're deployed. Upgrades are the upgradability pattern here is really used so that the proxy owners individually can upgrade their accounts if they choose to. That's a really dangerous thing to do. Like regular users should not upgrade their accounts. You'd lose support. Like for the Brink SDK, the Brink web app, you'd probably break your account in some way. But it's there so that if a new version of Brink, kind of like that account core, gets deployed someday, you have the option to, like all users of all the proxy owners have the option to upgrade to that. And that could be deployed by our team. It could be like a fork of the project. Like doesn't matter. Like you have the ability to upgrade to anything, and it's your choice as a user or as an owner of that account. So proxy contract is like the contract that defines the kind of like delegation of calls from your proxy address into the account address. Another huge advantage of doing this pattern is like if you upgraded your account, then your address, your Brink proxy address always stays the same. So you could have a totally different, like a Brink V2 or V3 or V4 or like a fork or whatever you upgrade to in the future. You're never going to lose the original address. So the original address will always remain the same. And this proxy pattern basically lets you execute anything that this implementation address allows. So implementation is like the account. What I showed you with account.sol, it is pointing to a deployed account.sol until you tell it to point to something else, which is dangerous to do. So don't do it unless you really, really, really know what you're doing. So it's just like kind of like a very small amount of code. The proxy, I think our gas cost for deploying these proxies is like, it's like 130K gas or something. It's very small, which is another huge advantage of this. So you don't, rather than like having to deploy all of account.sol for every time a new Brink user like creates an account, that would be crazy. Like account.sol is very expensive to deploy. I think we deployed like an earlier version of it that wasn't very optimized, but I think it cost like $300 or $400 in gas at the time, and probably would be even more now. I'm not sure, but this proxy account, could cost like at current gas prices, I think it's like a few dollars, maybe. It's very, very lightweight. So you can create a Brink account. It uses this proxy. You get all the functionality of that kind of core account.sol, but you're doing it through this like very lightweight proxy. So yeah, this just has like basically implementation pointing to the account.sol, the address of you as a proxy owner, and then this fallback to delegate call, which basically just means any function call to this account, no matter what it is gonna execute this delegate function, and that delegate function will execute within the context of your account, but it's going to use the implementation for its functionality. So it's going to execute on your account state, but it's going to use the logic from the core account.sol. So that's the proxy pattern that we're using, and I think a very common pattern. So I'll go back up. I think that's pretty much it for core. There is like, I guess I'll mention one other thing, but won't go through in too much detail. But this deploy and execute is here in this batch directory. Deploy and execute basically is like a convenience function that allows executors to like simultaneously deploy your account and execute execute anything on your account. So I guess I'll go ahead. Yep.
Oh no, you can continue that. We just had a question, but I'll let you.
Oh yeah. Yeah, let me just finish explaining this and then I'll answer the question. So yeah, it's good to talk through this because deploying your account is actually also permissionless. So anyone can deploy your account for you. Like you don't have to deploy the account yourself. Because if you are the owner of that account, basically your address determines what the account address will be. So like, it doesn't matter if like I deploy it or Justin deploys it or some random shadowy executor deploys it, you're going to get the same, you're going to have the same address. So the address is deterministic. So if I had sent, let's say I'd sent funds to that address, because I know that's going to be my address, and then I sign a message or I sign like a limit order that says like, I allow these funds to be manipulated if I can get this much output of another token. An executor could pick up that message and say, oh, well, I can profitably execute this based on market conditions, but I have to deploy that user's account first. The executor can deploy your account, then execute the message, kind of all in one transaction. So that's kind of the reason why we have this deploy and execute contract. It's, it is in core. It's like sort of core. It should probably just be in its own repo, to be honest. It's not really like, I see core as like the account core, but this is a pretty, like we use this for the executors that we've built. Yeah, you could have like many different versions of this. It doesn't matter as long as the accounts are getting deployed to the right place, which they have to be. Like they have to be deployed to the right address. If the executor deployed it, if they put in the wrong parameters, deployed it to the wrong address, they wouldn't be able to execute messages against that. So they can't actually manipulate your account in that way. Cool. So I'll go back up. And Justin, what's the question?
We had a question from my DeFi. Does the end user have the ability to set a max gas price for the operation to execute?
Does the end user have the ability to set a max gas price? So they can set it. It's a complicated answer for limit orders. Like and I'll go through how they work on the verifier side. for limit orders that you're not setting anything to do with gas price. You're just basically saying, I'll take, like, I'm willing to give up asset A in exchange for this much of asset B. So if the executor can source that, it doesn't matter. Like the executor worries about the gas. All you worry about is whether that trade actually happens or not. So in the case of limit orders, like, no, you don't sign a max gas. You just sign like what I want as far as the output and what I want for the input. So you can't get less than that. Now you could not get that. Like if gas is super high and your trade value is super low, then the executor won't be able to execute it profitably. So you wouldn't get it at all. Or if like gas is just high enough so that like the market price is there, like if in a market with zero gas, like it would be able to be executable, but gas is like, enough so that it's affecting that, like the executor can't source that trade for you because they have to pay the gas, then it just won't execute. So that's for limit orders. Now we've had this question actually a lot. You can develop other order types, and we will be doing this, where kind of like a max price might be a factor, like max gas price, but we'll try to make it so that, like, I mean, generally I think it's better if the user's not concerned about gas, they're just concerned about cost. So like you would sign like a minimum cost parameters or maximum cost parameters in terms of your order, but like not specifically for gas. But we could build an order type that is kind of like opinionated about gas price. It's definitely possible. So yeah, short answer, user doesn't have to worry about gas price. And hopefully for all the verifiers that we build as a team, the user will not have to worry about gas price, just like their order, the assets in the order, and the kind of cost of their order overall, preferably in terms of the assets within the order and not the separate like execution and gas cost. And thanks for the question. I'm glad we had a question. I know this is like pretty deep stuff here. So this is like a lot of detail. I know like our usual audience for AMAs is probably not going to be super interested in this, but I think this is good to live stream and good to have for the future. Okay, I'll jump over to Brink verifiers now. And we're trying to keep this like at an hour, right? I didn't even realize I've been going for 45 minutes. And I'm just not holding back on the detail. I'm going as deep as the contracts go right now. Well, I am holding back on some details, and it's still taking 45 minutes. Okay. So Brink verifiers, as I mentioned, are the kind of verification contracts for the order types. So we just saw like kind of the core super low level account, like signing, and how that works. Generally what you'll be signing is like one of these verifier contracts. But it could really be any contract, but we'll start with the Brink verifiers. So we have 3 verifiers. I'll just go through the limit swap one and the cancel one. Maybe I'll talk about the transfer one, but the transfer one's not quite as important. So the limit swap verifier, this is like the first verifier in Brink. This is how you do limit orders with a Brink account. So I'll say like, this is even just like one flavor of limit orders. Like you could build a different type of limit order and deploy that as a verifier. There could be hundreds of types of limit orders. Like these are just kind of like the 3 limit orders that we've come up with and that we've deployed initially, or that we will be deploying initially. So we have like basically 3 functions in this verifier. Token to token ETH to token, and token to ETH. So you could guess what these are. They're basically verifiers for limit orders for those types of swaps. So you have a direct token to token swap, an ETH to token, like native ETH to token swap, or a token to native ETH swap. And the reason why we have to have 3 is because we're handling limit orders that deal with like native ETH. ETH is not an ERC20, so we actually have like explicit functions here for native ETH. We could just have one, just the token to token, and use WETH for everything, or WETH, which is wrapped Ether. But we want to be able to support transactions that use native ETH and not have to burden the user, the owner of the account, with like extra wrapping steps. So we can support that with pretty simple 15-line function here. So less than that if you take out the spaces. Okay, so I'll go through. I'll just do token to token because that's at the top. And if I go through token to token, it pretty much explains the other ones as well. So I don't have to go through all of them. I'll just focus on this one. So this is verifier for a token to token swap. As you saw in core, we're verifying, or we're what you're signing when you sign this type of swap is, or this type of limit order, is the address of the limit orders verifier and the data for this specific call. And remember that partial sign data parameter, you're actually signing a portion of this call, and then that portion happens to be up to here. So if you're signing, you include this much data, then the remaining data in the call is kind of that unsigned portion that the executor is bringing. So what you would sign here is the address of the verifier. The bitmap index and the bit of this order are basically like a replay protection thing. So like this is like the unique identifier for the order. Once that bitmap index and bit gets written to your account state, this order can't be executed again. And that's important because you wouldn't want your limit order to be executed multiple times. If you sign it, like it becomes public. Once it gets executed, you need something to say, well, don't do it again. So that's what this is. And then you sign the input token and the output token address, and you sign the input amount and the output amount. And then an expiry block. So like you sign a block at which this order will forever expire. If you set that to like, the max value of uint 256, it's effectively like infinite expiry. It will never expire. But you could set that to like a reasonable block, like let's say 10,000 blocks from now, and it'll expire 10,000 blocks from now. Now, just a little example of like how you could build another limit order. Like you could do this as a timestamp expiry instead, and just deploy another contract like limit swap timestamp expiry verifier. And it's exactly the same as this, but with a timestamp based expiry instead of block based expiry. Slightly different, more or less the same, but then you have effectively like a new limit order type. And then that can get much more complex. You can build all sorts of different types, basically like any logic. But that's just a simple example of like, okay, this gets tweaked. And I could see like, a community user doing that. They're like, well, timestamp expiry should exist instead of just block expiry for whatever reason. So fork our code, tweak it a little bit, deploy that verifier, and now you have a valid verifier. Or now you have a verifier that does that. So anyways, back to the signing. So the user or the proxy owner would sign this portion of the call, the function name of the call, of course, and the address of the verifier. So that's what's in kind of like the message signature. And then this data is left over as like executor provided data, and this verifier handles this executor provided data in a secure way. So you can see where you get into trouble if you have executor provided data in a verifier, then and you don't and you're doing something unsafe with it, then the executor could like do some malicious stuff. So we want to just, all these verifiers are scoped to make sure that executors can only execute what the conditions that you signed, or what the parameters that you signed allow. So let's go through this now. So the first thing we do is just an expiry check. Okay, it's not if it is expired, then this reverts. If it's not expired, then we keep going. Then we kind of mark that replay bit, and I won't go into the replay bits library, but you guys can look at it if you want. Basically just like mark this thing as it's been executed, and we do that early in the function so we don't have a reentrancy issue. Like if you because there is some arbitrary call data execution here after this. So replay bit gets set. Then we store the initial account balance of the output token, because we're going to use this after the account is sourced to check how much output token was added to the account. Now this is the interesting part. So this is the part that allows this limit order to be sourced from anywhere. It's not, you notice like there's no like Uniswap call in here, or like balancer call or sushi swap call. Like this is completely up to the executor, like how this limit order gets sourced. So the way that works is first we transfer the token in amount to this address that the executor provided. So the executor actually says, just like, here's an address to send the what we call input token to. And it's kind of backwards here, because the input token is the token input to the AMM or the input to the source, and the output token is the token output from the source. So it's like opposite of what's happening in your account. Your account is like outputting the input token and receiving, I guess it's giving the input token, it's receiving the output token. So the executor says, okay, here's the to address. Just transfer the proxy owner's input to this to address, and I'm going to do something with that. We don't know what it is. And then the executor then executes, or they gave this data parameter. It's just like arbitrary call data. It says like execute this thing on that to address where we sent the token. So this just executes like whatever they provided. And then after that's done, we just do a balance check. We say, okay, well, what's in the account now? Is it enough? Like, is it enough token out? If it's not enough, then just revert. So if the executor provided this data and sourced it properly, then this check will pass, and then the user got their token out. If it doesn't pass, the whole thing reverts. So Ethereum transactions work. All the state gets rolled back. Nothing happened. So it's okay that this token in was sent, because if this reverts, then it's not really sent. So you can think of this like, if you're familiar with like flash loan concept, it's kind of like a little mini flash loan, like on the user's account. So it's like you're permitting this token in to be used for something, as long as the token out can be satisfied. So like with a flash loan, it's like a protocol would permit any amount of its assets to be taken, as long as that same amount of assets is returned at the end of the transaction. So we can safely do this, just like a protocol could do this with a flash loan. So that is that's how limit orders work in Brink. For now, we can build many different types of orders this way. You can see this, even this is like pretty generic, but we could build an Oracle-based limit order. So this one is like input and output based. We could build another limit order that uses a price oracle, and it is actually price oracle based. If our team felt that was like something valuable, but yeah, anybody can build a verifier, and anybody who owns a Brink account can technically sign to that verifier. Like we won't support those through our tooling at launch, but yeah, in theory, like if you're a developer and you're building something, you can really like use this to build any type of automation this way, or any type of like kind of signed conditional order. So I think that's, I'll go back and just talk about one more thing. I'll talk, because I have 3 minutes left here. I'll talk about this cancel verifier. It's a much simpler verifier, but it's the same concept. If you wanted to cancel, if you wanted to actually sign a message to cancel that order, you could sign a message that with these parameters and this function and the cancel verifier address, and then the that message will allow this bit to be overwritten. So that's like any limit order that uses this bit is going to be effectively canceled. So this is like just to show that these verifiers are pretty flexible. There's no incentive built into this one, so like it wouldn't really make sense to sign this. This is more like we can actually use this directly through like a delegate call. And that's another thing I should note is like the verifiers can be used directly by proxy owners too, to like execute these directly. Like they don't have to be used in like the meta kind of signed EIP 712 or EIP 1271 way. They can just function as like basically pieces of logic that affect the account. It doesn't matter if they're executed through like a meta call, through kind of a permissionless execution system with an executor that has a signed message that allows them to do that, or if you're the proxy owner yourself and you're calling them directly. Yeah, so that's pretty much like everything in core and verifiers that I wanted to talk about today. And
we did have one last question that perhaps we can cover before signing off.
Oh, absolutely. Yeah, I'll just stop sharing.
Sure. So I just displayed it there, but are there any measures to prevent front running or sandwich attacks? And can you talk about data sources for price feed oracles?
Sure, yeah. So front running and sandwich attacks in a system like this is more like something that the executors would need to worry about. So you as a user, like signing, like if you sign this limit order with a token input and a token output, like you can't really get front run at all, because you're basically just saying like, okay, this is the output that I allow, and this is the input I allow. And like, if it can be sourced, then it will be sourced. So do you care if it gets front run or not? I mean, front running is going to affect kind of the market for that. So it might like hit the market price and an executor can't do it, and then it won't get executed. So you might miss out on the limit order execution, but you're not, if it does get sourced, then it does, the fact that you got front run doesn't really matter, because you just said, this is what I wanted, and then you got it. So it's kind of like abstracting the front running sandwich attack issue away from you a bit, and then incentivizing executors to like kind of deal with that issue in order to kind of reap some arbitrage profits from your order, because that is how executors would profit in this system. So yeah, we're not directly doing anything to prevent front running and sandwich attacks. That's kind of like a lower level Ethereum and AMM issue. But we do have a system here that kind of abstracts that away from you. And then data sources for price feeds and oracles. I think for the orders that we use, that we create, and we will be doing this, that are Oracle-based orders, we'll be using Uniswap v3. time weighted average price Oracle. I think that's, I mean, I'm open to hearing about other Oracle solutions, but for like, and these are really like on chain. I'm calling it Oracle. It's not an Oracle like pulling data from off chain and putting it on chain. These are just like a way for Brink to verify prices on chain. So it's really an on chain Oracle. The Uniswap v3 time weighted average price Oracle is great because it allows us to like get a kind of unmanipulatable or less manipulatable price by giving basically a weighted average over multiple blocks. And that's how you get the price. So rather than like, using the spot price on an AMM or like using the current state of the, not the AMM, but the like an exchange contract, that's potentially manipulatable. Time weighted average price, less manipulatable because it's over like the course of a number of blocks. So an attacker to manipulate that Oracle would have to move the price where they want it to move for however many blocks the time weighted average price requires. So that can, in Uniswap v3, that can be like variable. You can set the required number of blocks, or required number of like Oracle reads, I think. So yeah, it's harder to manipulate price over more than one block. If you're manipulating price within one block, it's potentially very easy with flash loans, and if you're relying on everything within one transaction, it's extremely unsafe. And we've seen, I'd say like the majority of DeFi exploits are related to that, at least what we've seen in the past like year. The majority of major exploits have something to do with like price manipulation on AMMs and systems that are using on-chain oracles in the wrong way. So we're excited to start building some Uniswap v3 time-weighted average price Oracle solutions, which I think is like a better, not a completely completely infallible way to use oracles, but it's much better than like the way that oracles have been used in the past. So yeah, we're excited to build some of that.
Awesome. Well, those are all the questions we have received so far. Is there anything else, Mike, or should we end it there?
I think that's good. That's a lot of detail.
Okay.
Thanks for anybody who stuck around through that. I'm glad we have this. We'll put it on YouTube. Maybe someday I could do a more condensed version, but like this, yeah, this is like pretty much everything. So yeah, thanks everyone.
Yeah, thank you all so much for watching. All of our relevant links are going to be in the description. And we will see you all in the next live stream. If you have any questions that didn't get answered, just join us in the Discord. You can tag Mike or myself there, and we will get to them.
Cool. Thanks, everyone.